All right, welcome back. Today we are jumping into what is honestly one of the greatest scientific detective stories ever told. We're on a quest to figure out what the universe, what everything, is actually made of. We're going to see how our whole picture of the atom got completely flipped on its head in just a few short decades. So, let's get our investigation started. For centuries, people thought the atom was it, the end of the line. Just a tiny, solid, unbreakable little ball, kind of like a microscopic billiard ball. That was the idea from chemist John Dalton. But right as the 19th century was wrapping up, scientists started doing these mind-bending experiments. And the results, well, they just didn't add up. To explain things like electricity, the atom couldn't possibly be a solid little sphere. There had to be smaller, charged pieces rattling around inside it.
And right there, that's where our detective story really kicks off. The hunt was on. Scientists were searching for these hidden subatomic particles, and their very first clues came from, of all things, zapping gases with electricity.
Now, scientists already knew about the negatively charged electron. They found it using these things called cathode ray tubes, which are pretty much just sealed glass tubes that can shoot a beam of electrons. But some clever people modified the setup and noticed something totally new, a different kind of ray traveling in the opposite direction. These were streams of positively charged particles they called canal rays. And this was a huge discovery. It was proof that the atom had positive stuff inside to balance out those negative electrons.
Here's what was so fascinating about these canal rays. Unlike electrons, which are all identical, the mass and charge-to-mass ratio of these new particles changed depending on what gas was in the tube. This told them that the particles were actually the atoms of the gas, just with an electron knocked off. So they thought, okay, what if we use the absolute lightest gas there is, hydrogen? And when they did, the positive particle they got was the lightest one they'd ever seen. They realized this must be a fundamental building block of all atoms. And that little particle, in 1919, was officially named the proton.
So great. They found the electron and the proton. But here's a massive problem. Think about it. How could you possibly measure the charge of a single invisible electron? The number you're looking for is going to be so small it's hard to even imagine. It seemed totally impossible. Well, this is where the genius of Robert Millikan comes in. He devised an incredibly clever experiment to do exactly that. The goal was simple, but so audacious: to isolate one single tiny droplet of oil and measure its electrical charge.
Let's walk through how this brilliant device worked. First, an atomizer, kind of like a perfume sprayer, creates a fine mist of oil. These little droplets fall through a hole into a chamber. Using a telescope, Millikan could watch and pick out a single drop to track. Then he'd blast the chamber with X-rays. This knocks electrons out of the air molecules, and those loose electrons stick to the oil drop, giving it a negative charge. Finally, by applying a voltage to metal plates above and below, he could create an electric field to push the charged droplet up.
So the whole trick here is a beautiful balancing act. You have the force of gravity constantly pulling the oil drop down, but because the drop is now negatively charged, he could use the electric field to create an upward pull. Millikan would carefully, precisely adjust the voltage until that upward electrical force perfectly balanced the downward pull of gravity. And the result? The oil drop would just hover there, completely motionless, suspended in mid-air. Millikan did this thousands of times and found something incredible. The total charge on any given drop, which we'll call Q, was never a random number. It was always a whole number multiple of one single tiny value, which he called E. So Q always equaled N times E, where N could be 1, 2, 3, and so on. Think of it like this. A wall is built with bricks. You can have a wall made of 1 brick, or 2, or 100, but you can never have a wall made of 1.5 bricks. This proved that electric charge is quantized. It comes in discrete packets. And E was the fundamental charge of a single electron. Now get this. At the very same time all this was going on, a completely different team of scientists was stumbling onto another set of clues. They were finding out that some atoms weren't stable at all. In fact, some were spontaneously shooting out mysterious, powerful rays all by themselves. It all started by accident in 1895. Wilhelm Röntgen noticed that his cathode ray tube was producing some kind of unknown radiation that could pass right through paper and even wood. Because he had no clue what it was, he just called it X-rays. These rays were really strange. They weren't deflected by magnets like electrons were, but they were incredibly energetic. This discovery inspired other scientists, like Henri Becquerel and, of course, the legendary Marie and Pierre Curie. They discovered that you didn't need a machine to make these rays. Some elements, like uranium, were just naturally emitting this stuff on their own. They called this phenomenon radioactivity. It was more proof that the atom wasn't some unchanging solid thing. It could actually break apart and release a tremendous amount of energy. As they investigated further, they realized this radiation wasn't just one thing. When they passed it through a magnetic field, the beam split into 3 distinct types. They named them after the first 3 letters of the Greek alphabet: alpha, beta, and gamma. And as you can see, each one had a very different ability to penetrate through matter. Let's break this down real quick. First, you have alpha particles. These are positively charged. We now know they're actually just helium nuclei, and they're the weakest. A simple sheet of paper can stop them cold. Then there are beta particles. These are negatively charged. They're just super high-speed electrons. They can get through paper but are stopped by a thin sheet of aluminum. And finally, you have gamma rays. These have no charge at all. They're just a form of high-energy radiation, and they are so powerful you need a thick block of lead to stop them. Okay, so let's recap our evidence. Our scientific detectives had found negative electrons, they'd found positive protons, and they knew that some atoms could spontaneously spit out particles and energy. It was time to put all the clues together and build the first ever detailed model of the atom. The first suspect was about to be named. The man for the job was J.J. Thomson, the guy who discovered the electron. In 1898, he proposed his model. He said the atom was a sphere. But, and this is the critical part, he imagined that the positive charge wasn't a tiny particle inside. He thought the positive charge was a sort of diffuse, uniform cloud or jelly that made up the entire sphere. And then scattered inside this positive goo were the tiny negative electrons. To make this easier for everyone to picture, the model got a famous nickname, the plum pudding model. Imagine the cakey part of the pudding is that whole sphere of positive charge. And the little plums, or raisins, scattered throughout, those are the electrons. Another great analogy is a watermelon. The red fleshy part is the positive charge, and the seeds embedded inside are the electrons. So how did this first draft of the atom hold up? Well, like a lot of brilliant first ideas in science, it was an absolutely vital stepping stone. But ultimately, it was flawed. It was wrong. Now, its biggest success was that it perfectly explained why atoms are electrically neutral. It was simple. The total positive charge of the pudding was perfectly balanced out by the total negative charge of the plum electrons. It was elegant, but its failure was a big one. It just couldn't explain the results of some of the newer experiments that were coming out. The idea that all the mass and positive charge was just spread out evenly simply didn't hold up. But this era of discovery gave us our fundamental cast of characters. We have the electron, which is incredibly light with a charge of -1. The proton, almost 2,000 times more massive with a charge of +1. And finally, the neutron, which was found a little later with no charge at all, but about the same mass as a proton. These are the building blocks that Thomson's model tried to organize for the very first time. And let's be really clear, even though his model was eventually replaced, Thomson's contribution was absolutely monumental. He won the Nobel Prize for his work, and it laid the foundation for everything that came after. This is a perfect example of how science really works. A flawed model, a wrong idea, can still be a giant leap forward. So the plum pudding model was a vital first step. It gave us our first real glimpse inside the atom, but it was a picture that was about to be torn to shreds by new explosive evidence. And that leaves us with a critical question. If the atom wasn't a sphere of uniform pudding, what did it really look like? We'll dig into that next time.